Okay, so just my interests are in power grids. Now, just a bit about the research that we're doing. So I was very lucky that Vili allows me to sort of look at what grids can be as opposed to what they have to be. So we're looking at what's happening with the world, where's energy taking us, and what can a grid become as opposed to how can we bring these existing energy sources within the grid as it currently exists. And there's quite a few things that you pick up on, and interesting little niggles, that issues that we currently have that maybe we can solve if we just look and approach the problem from a somewhat different angle. And so that's where VSGs and synthetic inertia comes in, because in a certain way it's a way of reproducing old technology within a new system, bringing new technology to work as old technology does. But it also provides a very vital component that we can utilize in moving forward. So that's the basics of what I'm studying and what I'm interested in. So, as I told you, we're experiencing a significant shift in the way that the energy that we obtain comes from in the world we live in. So on the left is a machine which we'll look at a bit further into the presentation, which is a synchronous machine that exists within VITS, which is currently it's set up to can do about 160 kilowatts if we push it. On the right, however, is the VITS solar, the installation sitting on top of the lab in Gemini Labs, and that's rated at 140 kilowatts. So, you know, similar sort of power ratings, very different scale, and obviously very different ways that you interact with it and use it. So the one thing that's come about lately is synthetic inertia, and it's sort of become a bit of a buzzword, because typically as we introduce these new sources of energy, we're reducing the amount of inertia-based generation that exists, so rotating generation that exists. And there's certain benefits that come with that rotation generation that we're sort of now seeing, that as we start removing it or replacing it with electronic inverter-based generation, we're running into a few issues. When we recently were on a trip to Germany and we spoke to universities in Hanover and Paderborn, they speak about this weird curve that as you decrease inertia-based generation, you reach an instability point. So if you're going from a mechanical system towards a more electric system, you can run into instability problems. I think it was roughly at the 60% or 40% penetration. Whereas if you go from electronic grids and you start incorporating rotation machines, you also run into a similar problem. So in this presentation, I'm going to provide a bit of background about power system inertia. Not so much how it's useful, but what is it and how can we look at it and think about it when we look at a power system in terms of just a very brief modeling point of view. We're then going to look at how can we synthetically increase the inertia of a machine, in particular a synchronous machine and an experiment we used at VITS. We're then going to move on to what happens within an inverter, what actually happens within a generation. So to do that, we're going to look at the DQ modeling, or specifically the space vector modeling that we use in order to make this inverter look like a machine. We're then going to talk about how do you then get that inverter to emulate inertia, how many different orders of implementation, what elements of a synthetic machine do you want to have and can you have within an inverter, the benefits and disadvantages of doing so, and then we'll conclude and open the floor up to some questions. So the inertia, and I think everyone in this room will be very familiar, is typically your inertia comes from your Drupe equation, which is your inertia acts as almost like a fast responding storage to changes in your generation and load. So your prime mover doesn't instantaneously have to now provide the energy that your load's now drawing. There's a bit of time for it to respond, and obviously the larger your inertia, the more time your prime mover has before you start running into frequency issues. Now, what we also have is that when you start putting generators at the end of what's called a weak grid connection, which is where the start of a lot of the microgrid research as we currently know it, you do need to have local inertia in those, you've got local inertia, but selecting the right amount of inertia can be critical. And so there's a lot of research, for instance, in virtual inertia found that if you can vary your inertia, you can actually improve the stability of a system with generation. And as I mentioned earlier, the electronic generation we're seeing today, the solar panels, which are predominantly a bit more predominant, specifically in Africa, does not by itself add inertia, at least not currently. Not the way we've currently implemented it. So, as I said, in Germany you can run into frequency stability issues. So from a very basic modeling point of view, when you look at a bunch of synchronous machines connected in parallel, you can, in effect, look at them as if they were one machine with a single larger inertia, which is the sum of all their inertias. There are complications when you get to it, but for your bare basic modeling, and it's been generally acceptable within research, you can look at your inertia as a sum, as a large sum of inertias spinning together. So how do we go about increasing the inertia? So you can add a bigger flywheel. That's a bit difficult. However, we wanted to increase the inertia of that synchronous machine on the left, which, due to its build, has a fixed amount of inertia. We then attached onto it a prime mover and a variable speed drive controlled with a PLC. Now, you will notice that prime mover is significantly smaller than the synchronous machine. That's a 70 kilowatt synchronous machine and a 5.5 kilowatt prime mover. So what we do is we then set the variable speed drive to maintain a constant set point speed. It will then report back on the torque that it thinks it's using to maintain that speed. We can offset that power and torque by introducing an offset, and then we implement a discrete version of that control loop, which gives us this result. So what we did here is we allowed the machine to spin down from 1500 RPM without any load or excitation, so the power coming off is simply purely off friction, and we just let it run down for various amounts of emulated or virtual inertia. And you can see the spin down time does increase significantly. Now, there are errors present in it, largely because we have a slight misalignment issue with the two machines. So the torque measurement has a huge fourth harmonic, but it does the business. There are errors in it, as well as the energy needs to come from somewhere. So that's the biggest thing about virtual inertia, is conservation of energy must still be maintained. So whatever energy you would have from having a larger flywheel, you now need to supply from capacitors. If you're using wind turbines, they'll use the rotor blades, the actual inertia of that rotor blades, and slow them down significantly more than they would normally be. But that energy, conservation of energy, needs to come from somewhere. So now that we've introduced what inertia is physically, well, you're all familiar with it, we've looked at now how you can emulate that inertia using the machines, or how you can make a machine appear to have more inertia. Now we can talk about what's going to happen when we actually do throw it into an inverter. And that particular inverter is currently bane my existence in the lab, but that can emulate inertia, and it does sort of look the same as that synchronous machine to its left. So your basic inverter stack consists of a DC input, 6 switches, some sort of filtering, and then some feedback of the voltages, the currents, the power. Now, what you then take is, in order to avoid shoot-through, there's only about 8 possible states for those switches. We map those states in. We then apply a stationary park transformation to it. So we take it into the to the D-axis and the Q-axis, and then we get this potential plot. So if we wanted to produce a desired voltage out of the inverter, we can map it to a combination of switch states, and then just vary how long we leave one switch state on versus another, and that way we can actually produce a rotating voltage. So with a normal inverter stack, it is possible to create what appears to be a voltage. Now, when you look at it, change your modeling perspective a tiny bit, you can then have it going through some form of filter inductance. That filter inductance looks very similar to what a synchronous machine, that typical EMF behind an inductor or an EMF behind an impedance model. You can then also, with the software of an inverter, add virtual inductance. So you can actually, even though you've got a largely resistive network, such as what you get in 400 volt power systems, you can actually still ensure that you have inductive coupling between voltage sources, which means that you can still use your decoupling assumptions of reactive and active power, and then maintain your standard group control elements, that PF and QV. So we now come to how must you operate an inverter in order to obtain this sorts of characteristics. So there's two general types of inverters that we've been using for a while. Current source inverters are a bit older, simply because you could use thyristors, which were at the time a lot cheaper and more powerful for what you were getting. However, now, because of improvements in technology, reductions in costs, we can use switch mode devices to now produce an EMF behind an impedance. Whereas with a current source inverter, you can only inject current into an existing source. So then the question comes down to what dynamics do you want to emulate within a synchronous machine? So if you've got a synchronous machine, what dynamics do we want to emulate? Because now we can actually pick and choose what dynamics are useful, what dynamics do we want to dismiss, what can we create a grid from, and what can we get away with. So there's a variety of orders of the synchronous machine that you can incorporate within the inverter behavior. The most common one, which is the one that we've been using for a while, is just the microgrid truth controller, which simply emulates that friction element of your synchronous machine. Now, that's a common approach. It's thought to generally improve stability on the grid system. However, if you use discrete measurement techniques to measure the frequency, which you then implement that droop, you can run into stability problems. The next one is first order emulation, which is used a bit, but you can't really you can't really operate a grid with islanded. It sort of relies on an existing voltage to exist in order for it to. It applies a derivative to the existing frequency that it measures and then adjusts its power output appropriately. The next and most useful one is a second order model, where you just consider the mechanical dynamics of that, the swing equation of your normal synchronous machine, and then you make that happen within the inverter dynamics. And from this, you can actually start setting up what looks in its most basic element to be a synchronous machine. And so you're able to do black start facilities. You're able to just synchronize it. Same way you do nowadays with just about any synchronous machine generator. You can operate it standalone, or you can synchronize it to an existing system. And then you can make it more complex depending on what it is that you wish to add into it. So, for instance, if you did implement virtual impedance, you would then start looking at a third or fourth order model where you start including the windings. So, as I said before, your synthetic inertia is simply it's making your inverter now respond to changes in frequency, or you can now have the frequency changes response to loading changes. However, you still need that energy to come from somewhere. And as what happens with a DC, with an inverter, it comes from your DC. And if it's coming from your DC, that means the energy is coming from your capacitors. And so one of the implementations of this synthetic inertia was they ran the inverter in an open loop system, but they changed the output frequency that the inverter was producing. So essentially the effective speed of that machine, of the inverter, as a function of the bus voltage on the DC caps, which again is consistent with the conservation of energy, which must at all times be maintained. And then because you've got now this, you're essentially implementing still a synchronous machine, you can now do all the other things that we do with synchronous machines, such as providing reactive power support, QV droop, as well as having some form of secondary response programmed in it. So some of the issues that come along with their existing inverters is their ability to synchronize, and how do they get themselves to inject their current or their power at the appropriate phase angle. And the common techniques, which is used quite a lot in literature, is to use a PLL. So your standard PLL locks into the frequency via a feedback loop, and uses some sort of error to detect the angle between the outside waveform and the inside waveform. Now, you do need to filter it. That filter inherently adds a delay. So specifically when you're dealing with inverters, all of a sudden you're also going to be seeing a lot more noise in the voltage. So when you start seeing more noise, you need a bit more filtering. So typically, I think the shortest I've seen in literature was someone managed to do 100 millisecond sort of filter response. Now, if you think about it with modern systems, as I said, you keep reducing that amount of inertia. That frequency might change a bit quicker than and then 100 milliseconds, you might run into a very sharp frequency change that you can then run into an instability when your inverters are now actually absorbing power instead of supplying power, simply because their internal phase shift's now off from what the grid actually is doing. So what you can do is you can actually start using the hardware as that feedback loop within it. This is a very similar principle to what your synchronous machine does when you do actually synchronize it with the grid. If the grid advances, your synchronous machine will absorb power and therefore will advance as well. So you're doing the same dynamics, you're just now doing it within this the rotating vector which sits in software. So there's a bunch of technologies which have come out demonstrating this sort of PL-less approach. Synchroverter, inductverter, you find that people like to coin their own terms, especially in the green energy field. If you can coin a nice term, you can sell it better. But one of the biggest advantages for us was that if you lower the computational requirements, because now you don't need something that's actively sampling on the ADC, trying to measure where the PLL is and do those sorts of corrections and filtering, you can actually improve the inverter response to get, in the case of that inverter I was seeing like 10, 20 milliseconds response times to changes in frequency. Because it's just it's almost an open loop model where you simply have an internal voltage which rotates, and then based on the instantaneous power out, which is just simply you sample your voltage, your currents, you multiply them together, and then that's your active power out. You just integrate that and then change the speed at which your internal voltage vector rotates. So you can now implement much faster control. The idea for that came from someone mentioned that how do you measure frequency? There's 3 ways of measuring frequency. The first way is your zero crossing technique, where you count the period between your zero crossings, or if your frequency is fast enough, which it isn't really for grid operated devices, you count the number of pulses within a given time. The second way is to use a PLL, where you try and track it, or some sort of Fourier technique, which obviously is going to be a lot slower. The third way is you connect a synchronous machine to your grid and you measure the speed of that. That's actually where the idea for this came from, that you can use the inverter now. Since you can make an inverter look like a synchronous machine, there's no reason why you can't now make the inverter, which looks like a synchronous machine, also much more quickly measure the frequency despite noise and ripple, which you're inherently now going to have. So for instance, the system where we were testing it on, each inverter was putting out a total current harmonic distortion about 90%, and we've seen on the voltage, because of that big synchronous machine, about a 10% total harmonic distortion. So it's quite robust to noise, as opposed to your normal PLL technique. So of course there are quite a few benefits from using a synchronous machine, using an inverter as such. And what we're finding in grids as we're developing, so this is where the fields of research around microgrids, milligrids, nanogrids are actually developing, is you're going to have, so a microgrid is a localized system of generations and loads with some form of control and a downlink to a common sort of point of common coupling to maybe a grid or something to that effect. And what we're finding is as we add the solar panels into these grids, they're running into issues such as how do we provide other services. So it's not now just about selling kilowatt hours, it's about selling VARs, it's about selling frequency support, about selling, there's a word for it, but peak load demand. That little duck build, which we're seeing a bit more, which is when the solar cuts out, you've now got your morning and your evening load, which now increases. So your local system is now seeing very high transients of power load, as well as harmonic filtering. So you can actually do active harmonic filtering. Group, I think it was ABB for wind farm in the Netherlands, if memory serves, did a talk on that when we were in Denmark. So you can actually provide these services now with your electronic converters, which dynamically have few differences, can have few differences to your synchronous machines. You can provide protection a lot quicker, so you're not reliant now on a mechanical device to open and then the arc to be extinguished. You actually can turn off the current going out. And so you're actually able to implement protection a lot quicker than you would with normal mechanical breakers. You can then, which is the interesting one, vary otherwise constant parameters. So there's no reason why the inertia on your grid or the inertia on your generator needs to be a constant. Because you're setting it in software, as I showed you earlier, you can actually dynamically vary it as time progresses. And so you can start now making it bigger or smaller depending on what your needs are. And in 2015, a group showed that if you've got a generator at the end of a long transmission line, if you have a large enough transient, you can cause an instability. However, if you vary the inertia, so you make it small as the frequency deviates back towards 50 and larger as the frequency deviates away from 50, you can actually suppress those oscillations and actually bring the system back down. In a recent magazine article in What Now, someone was actually speaking about it, that we can actually turn around and set the inertia to be 999 or 10,000 or whatever you need it to be during a fault, and that way the frequency doesn't need to change that much during your transient. So you can keep the system running for a bit longer. As well as now you've got an inverter, it's intelligent, you can include diagnostic capabilities on the inverter itself, so communication, send an SMS back, so instead of City Power relying on Twitter, hey, my power just went out, the thing can actually send a message back saying, hey, power just went out, and that way you can actually speed up your response. Obviously there are disadvantages of using inverters, and there are a few issues which do need to be dealt with. The first one is that each inverter, as I said, has that filter. Now when you start adding these inverters in parallel, that capacitance starts adding up in parallel, and so that resonant frequency of that LC combination starts moving lower and lower and lower, and might actually now get excited by, say, a switching event, load change, or something to that effect. You can also get interactions between the control loops, where just because of a time delay, the one control loop might feed another inverter's control loop, and you can run into issues like that. And so this is where we start looking at master-slave topologies, where you've got one guy making most of the control decisions, everything else just follows, or a central control technique. The other and the big one, which a lot of people see when they think about inverters, is the fact that now your fault currents are significantly larger. So when you're dealing with a big synchronous machine, that magnetic core provides you with a very large thermal mass, so you can actually sustain quite large fault currents for a significantly larger period of time than you can with an inverter. When you build an inverter, your IGBTs, fairly thin piece of copper, your heat sink, fairly thin. We want the whole thermal system is designed to take as much of the heat out as quickly as possible, as opposed to storing it locally, which would allow it to operate a bit longer. So maybe you can look at, but as I said, if your protection can act quicker, there's no reason to enable these fault currents to go on for longer. There's no reason why we can't change it. But again, it speaks to we actually need to see a bit of a paradigm shift in the way that we look at what the future grid looks like, as opposed to trying to get these systems to work within an existing grid. So that's where the freedom of saying what does the future grid look like allows you to look at these problems and say, well, that might be a problem now, but how can we solve it in the future? And obviously, with an increased system complexity, because you've now got a lot more devices, you've got switching devices, microcontrollers, you lead to an increased risk of failure. Because you can now start using inverter stacks more frequently and more common in your power grids, there's actually a bunch of technologies which have come out recently, now DIRs, which actually very much broaden the scope of what we can do with the future grid and how we can solve problems in the future. So the first one is that Mercedes and BMW and a few of the big German electric vehicle stakeholders are looking into LV and medium voltage within city centers for electric vehicle charging, because as Mercedes says, if you're trying to charge a car with 100 kilowatts, it's a lot more efficient just to have a DC line coming in that you can then control, as opposed to having an AC line that you've then got to rectify, change, and charge the car with. You can also then, for neighborhoods, you can have a solar connection. Instead of your solar power panels needing a DC to three-phase inverter, you can actually run it through DC. Now you might be wondering where that comes from. And that's these things, solid-state transformers. So if we're getting rid of generation with inverters, there's no reason why the good old transformer needs to remain in copper around a magnetic core. So very recently they're looking at solid-state transformers where you've got high voltage AC comes into a stack. You'll then have a DC to DC converter in the middle, and AC will come out. And now if you think the way I do, the benefits now become enormous, because now you can asynchronously couple power systems. You can have one power system that needs to run exactly at 50 hertz, running all the time at 50 hertz, whereas your other one varies as it needs to. You have tapple points for your DC, so you can incorporate DC within neighborhoods and microgrids, milligrids, and all that fun stuff. You can now very precisely control the active and reactive power transfer from the one side to the other. You can also implement your fast protection, so you don't need to worry about slow protection. You can isolate a neighborhood fairly quickly, and again, deal with it. And you've got the localized intelligence to help out. So, in conclusion, from everything that we've done so far, your inertia represents a storage of energy. And that's what it's been, and it's been a very vital component in the way that we think about grids, the way we look at grids, and the way that our grids have been managed for the last 130 years, I think it is, since the 1880s, 1890s, where Edison and Tesla were battling it out. However, as we start adding in electronic generation, we've been removing that inertia. So we've been losing a component that we haven't really thought too much about. It was sort of a component that was there and something we had to deal with, but its benefits weren't that well understood for the time, and so we started removing it. So it's possible to emulate more inertia physically. We just need to have a source of energy to do it. And likewise, you can then do that with your electronic inverter stack. So you can emulate a voltage behind an impedance. You can then emulate various dynamics of a synchronous machine. And the nice thing is you can pick and choose those dynamics which assist you to build a system and discard those which add headaches and problems and control issues, as well as varying them. So you don't need a fixed inertia. You don't need a fixed amount of droop. You can actually change it as you need it. And so you can actually scale a system a lot more easily and change parameters and debug issues quite quickly. You don't need to physically swap out a flywheel. You just simply change a number in a computer. You can then use, because you can get the inverter to look like a synchronous machine, we can use it the way we've been using synchronous machines for the last 120 years, where you can use it as a standalone device. So a little petrol-powered generator, for example, or something to that effect. Or you can use it on a synchronous, on a grid level, where you tie and synchronize that inverter to a local grid. You can then also, because the technology is that advanced, decouple your AC systems, and so you no longer rely on a synchronous connection between the two sides. And so a lot of the dynamics and issues that we experience around having two synchronously coupled synchronous machines, actually, so that if you've got the inductance, the sub-synchronous oscillations, you no longer need to worry about. Obviously, the big disadvantage is your lower fault current, so we need to start rethinking the way the protection works. So I just want to end up with one of my favorite quotes, which was one of the things that drove me into the field of research, and one of the things I've got to keep in my mind the whole time. So this was Gus Speth, who was a co-founder of the Natural Resource Defense Council in the US. And the thing about it is we've come up with all these great ideas when you're always presenting new ways of thinking about it, new ways of bringing in renewable energy. But we're always fighting the fact that we've got to convince people that this is useful, that this is something that is not going to change their life that much. And we look at what happened in Cape Town. People weren't too concerned about water until they were told, you're not going to have any water. Currently, we're not too concerned about what the energy grid's going to do because we still have coal. It's only when we start hitting like a few years from D-Day when, well, there's not going to be any more coal, in a few years, so, start managing it, that people are actually going to wake up and look at the problem. But that doesn't mean we can't look at solutions for the time being. Thank you.
Jarren, thank you very much. Any questions for Jarren? Rob, it's a general question. I apologize for my ignorance. Are there any limits that define microgrids, nanogrids, and that in terms of power or whatever? Today's the first time I've seen milligrid.
Well, that's actually one of the biggest bones of contention I've got. There's actually, because of the way that the grids are currently developing and the different power requirements, you've got China and Asia looking at different solutions to what Europe's looking at, to what America's looking at, and then Africa's sort of lagging behind as far as this development goes. And so you've got a SIGRED definition for microgrids. Another group, I think there was an IEEE definition, and then China's got its own definition for what a microgrid is. So the answer to your question is not really. The problem is the way that it's defined. It's this very loose definition, and so a lot of people are grabbing onto the buzzword of microgrid and throwing it around and saying, hey, look, this is a microgrid. Hey, look, this is a microgrid. The core of a microgrid was when you start running into a loosely coupled system. So you've got a long transmission line and then some system with its own localized generation and load, which is what is happening. People putting in wind generators, solar generators. All of a sudden you ran into voltage problems because that transformer, which you normally run to supply power, and so you've adjust the winding ratio so that it ups the voltage a bit, is now pushing power the other way. And so now you've got like voltage transients in that localized sector. And so that started the idea of what a microgrid research. So to the rest of the world, microgrid research is at a long line. You've now got some localized generation and you can run into problems. So how do we control that system so that it can run while grid-tied and run while islanded? Typically, we're talking about, we're talking shopping malls, neighborhoods, so those sorts of power levels. So, maybe a couple of megawatts to, 100 megawatts sort of thing. Milligrids is then what you'd start looking at like cities. So a milligrid would be a city. So city power would be like an example of a milligrid, except it's got multiple points of connection. Microgrid, as we've handled, there's then nanogrid, which is now a household. So, a household, and then they've even got a picogrid, which, depending on WITS's definition, which is a low voltage system, because that was the term that was coined. Europe, however, turned around and said, no, your picogrid's now your car, for example, because you've got a localized generation, localized storage, and your loads. So, sorry for the long-winded explanation, but there's no nail on the head, this is what it is. The problem is you're dealing with a very competitive field, and so, everyone's trying to throw out flashy terms to pull things in. What we're looking at WITS is remote islanded power systems. So that's the SIGRE definition. We originally started calling it microgrids and then ran into some friction when people are like, but that's not what we call a microgrid.
I'll see the latest. The first Porsche electric vehicle, they're going to use 800 volts as the bus voltage, which is quite high.
Yeah. It's an interesting thing. It's just so, for instance, if we go back to my quote earlier, and this is the one contention I've got with electric cars. 90% of people do, I'm sure everyone in this room does about 50 kilometers a day on average on their car. That's sort of your typical to work and home. Maybe a bit of shopping. You don't need a full-sized car to do that. So, a friend of mine bought an electric bike to do his 10K commute in and out. That thing has the potential to do 50 kilometers. The thing weighs 10, 20 kilograms. You're obviously using significantly less energy, but no one wants to hear that. For some reason, we want electric cars that do 600 kilometers. For some reason. And that's the problem is, that's the thing. And that's why it's human greed. We don't want to go forward by going backwards. It's until something happens like what happened in Cape Town that we actually okay, electricity, energy. So the one example I use is, why don't we shower in the middle of the day when the sun's out? Just think about that a bit.
Just in terms of security.
I beg your pardon?
In terms of security.
Yeah. Security. In what regard?
In terms of cybersecurity.
In terms of?
Cybersecurity.
Yeah, that's why I disagree with what I'm seeing overseas. So Europe and America wants to centrally control everything. So they're looking at how can we get everything to talk together. The actual aim of my PhD is what's called decentralized control. So you actually have a bunch of elements that can independently make decisions regardless of a communication network. And so you can actually eliminate that cybersecurity variable. So my thing, because I used to, before Anonymous, I used to play around like that. If someone wants access into your network system, there's nothing holding them back. If they actually want to do it, someone who knows what they're doing will not have a problem doing it. Whether they use social hacking, network-based hacking, or however it happens to be, they can get access into it. There's nothing that's uncrackable. It's just how dedicated does someone need to be to make it there.
Jarren, tell me, how possible is it to
That Okay, so if you're using a voltage source converter, so in other words, something which already has switching devices, IGBTs, MOSFETs, or something like that, you can actually reduce the computational load of the system by implementing this algorithm. The issue is it's not what people have been doing. A lot of people have been, oh no, we've got an existing grid, we do it like this. This sort of thing can actually be done quite easily. You don't physically change a lot. So for instance, my misadventures into it began when I tried to build my own inverter, and the D-space components we were using, the PLL wouldn't work. It kept giving me nonsense, so the PLL wouldn't track on it. So my idea was, well, if a synchronous machine doesn't need a PLL, why does my inverter? So you can actually reduce it and improve the performance of it. It just needs feedback on what's actually going out. So it needs some form of feedback on the actual power going out or the DC bus voltage. It depends.
Okay, you may have touched on it a bit. I'd just like to know more about it in terms of with renewable energy penetration. There's a level at which you may start experiencing stability issues for your existing systems. You mentioned around 40%.
It varies. It depends on the...
It would be interesting to know what that level is for the South African grid. And this, which I think is basically the solution you're having, where do you see that level or this pushing that level to?
Okay, so my understanding of the inertia problem, and so I've only really replicated it in small scale. If we've got time, maybe I can show you it. Is it actually comes from that inherent delay of measuring the frequency that your droop devices respond to. So when you've got your droop controlled inverter, it's going to respond after a certain amount of time to a change in the frequency. So you might have the frequency start going down. Your row-off might be quite quick, or your disturbance might be quite quick. And then if they don't measure that frequency quick enough, they might not start exporting the power. And then by the time they do, the system's already recovering, and now they're pushing it further. So you get sort of a positive feedback effect happening because of that delay, at least in the small scale that I've observed. And so part of it is that delay because you're using a PLL or some sort of filtered technique to measure the frequency. So that's where, and I get my roughly 50% from it. It's actually like a bunch of maths and quite nasty, but I can show you if we've got time, if they'll allow me to. As to pushing it further, so part of it and part of the synchronous machine, and the reason I mentioned the PLL-less based inverter schemes, is they have the possibility of operating on a much, much quicker response time. And because you operate them in almost an open loop sort of way, so you operate them as if they're a voltage source behind an impedance as opposed to a current source, which is what we currently look at them. They're currently like a power injector as opposed to a voltage source. You can actually, in my, theoretically from what I can see, run it at 100% inverter based, or continue linearly all the way through.
If you have sufficient storage, because you need energy, you don't just virtual inertia. You need energy to make it work.
Exactly. That's why I stressed that several times. Is conservation of energy must be maintained at all times. We can't run away from that, no matter how much big oil apparently is trying to stifle it or something. So yes, you do need bigger caps, supercapacitors, a flywheel. I remember at the SAIEE a year ago, someone was saying that they'll slow down the wind turbine. So they'll draw the energy from the inertia on the wind turbine. The energy needs to come from somewhere. That's, the end truth in the matter. The whole issue about storage is another one of my things of, I don't like storage. I don't like batteries. They generally, the cycle life puts me off. They add to your footprint instead of removing it, whereas your solar panels actually tend to reduce it. So my vision of the future is a system with as minimal batteries. So your system might go dead, but you'll have those devices which you need to run all the time will have localized storage as opposed to grid-side storage. The idea of grid-side storage is humans don't want to be told, okay, we're turning the power off between 10 and 4 in the middle of the night. You try and say that to people, there's going to be an outcry, even though most people are asleep. It's the same thing if you tell people, right, we're replacing all your cars with a car, they'll do 50 kilometers a day. Most of them won't feel it. But they'll complain because you've taken something away from them. And that's where, like, for instance, what Tesla did in Australia. I was like, you're just pushing that idea that, just throw a bigger battery in it. It's the old American adage. If you can't get the car to go fast, throw a bigger engine in it.